Welcome to the Water Resources Podcast. I'm your host, Bridget Scanlon, from the Bureau of Economic Geology at the University of Texas at Austin. This podcast is produced in partnership with the National Academy of Engineering. In this podcast, we discuss water challenges with leading experts. I'm pleased to welcome Junguo Liu to the Water Resources Podcast to discuss global and regional water, energy, and food issues. Junguo is currently the president of North China University of Water Resources and Electric Power in Hunan province. He received many awards and was recently elected to the Swiss Academy of Engineering Science and is a member of the Academy of Europe and World Academy of Arts and Natural Sciences, and also a fellow of AAAS, American Association for Advancement of Science. So I really appreciate Junguo taking the time to talk with us today. And his main research interests include hydrology and water resources, global environmental change, and ecological restoration. So today we're going to focus on Junguo's research in global and regional water scarcity assessments, food production considering water and fertilizer inputs, and ecosystem services. Junguo's work also emphasizes mitigating water and food scarcity through food trade. So thank you so much, Junguo, for joining me today.
It's a pleasure to have a talk.
Okay, thank you. So Junguo, let's start off with the water scarcity discussion. And you wrote an excellent review article on water scarcity that provided many insights and highlighted many of the issues with quantifying water scarcity, focusing primarily, I guess, on water quantity issues, but also considering the importance of water quality and environmental flow requirements. So would you like to describe some of that work, Junguo, and how it has evolved over time?
Thank you for mentioning our review paper on water scarcity. Understanding water scarcity is very important for developing policies at different levels. Since the late 1980s, when water scarcity became an issue, many indicators have been developed to assess water scarcity worldwide. I would like to first introduce a few indicators for the quantity-induced water scarcity assessment. The first indicator was introduced by a Swedish scientist, Professor Malin Hockenmark, with the concept of per capita water availability. This approach, known as the Hockenmark indicator, measures the volume of water available for each person. A threshold of 1,700 cubic meter per capita per year of renewable fresh water was used to indicate water scarcity, and below this threshold, different levels of water scarcity occurs. When water availability drops below 1,000 cubic meter per capita per year, it indicates high water scarcity, and below 500 cubic meter per capita per year, it denotes absolute scarcity. The Hockenmark indicator offers a straightforward method for evaluating water scarcity with readily available data for assessment. The water use to availability ratio, also known as the criticality ratio, serves as another commonly used indicator for assessing water scarcity. It quantifies the amount of water utilized relative to the available renewable water resources. And according to this ratio, high water stress is identified when water withdrawal surpasses 40% of the available water resources. The third indicator I would like to mention is the EMI indicator, developed by the International Water Management Institute. And this this method integrates both physical and economic aspects of water scarcity. And the physical water scarcity means countries unable to meet projected water demand, even with national adaptive capacity considered, while the economic water scarcity refers to countries with sufficient renewable water resources, but requiring significant investments in water infrastructure to make these resources available for consumption. The last indicator I would like to mention is the water footprint-based approach. Many water scarcity studies primarily use water withdrawal to assess water use, but ignore the fact that return flow can be further used by downstream users. To address this issue, Professor Hofstra introduced a water footprint-based approach for global water scarcity assessment. And the water footprint quantifies the amount of consumptive water use in the production of goods and services that will not be further used by downstream users. So maybe I first give a brief introduction about these indicators at this moment.
Right, yeah. So that's great. So Malin Falkenmark from Sweden was the first person to introduce the concept of water scarcity, and she based it on how much water was available for humans. And I assume that that included food, water used with the food that people eat. And so adequate water availability was 1,700 cubic meters per capita per year. And for people in the US that often think about gallons, that's almost 500,000 gallons of water per capita per year. But keep in mind, that's not what you drink or what you shower with, but that's mostly used for irrigated agriculture and food production, right? Because Stefan Siebert mentioned that, 70% of global water withdrawals and 90% of global water consumption is used for irrigated food production. And so that's the elephant in the room. And Junguo, you also mentioned an important concept. So the concept of water withdrawal versus water consumption. And so when people talk about water withdrawal, it's how much water was withdrawn, but much of it could be returned to the source. For example, in the US, one of the biggest water withdrawals is for electric power. But 98% of that water is returned to the source, which is oftentimes rivers, but at an elevated temperature. So it's not consumed or lost to the system by evaporation or transpiration. So how we calculate these numbers is very important and impacts the values we get for water scarcity. So I think it has evolved over time. And so the water footprint then that focuses on consumption, I think is more realistic maybe than considering water withdrawals. So a lot of these water scarcity estimates are developed on a grid scale, global analysis, 50-kilometer grid scale. And originally, most of them were based on annual timescales. But more recent estimates then consider a monthly timescale. And considering higher time resolution then has generally resulted in larger numbers for water scarcity. And since we're considering water supply versus demand, then more recent studies also consider not just the water demand for humans, but also for ecosystem services. So fish, aquatic ecosystems and other ecosystems. And they oftentimes use an estimate of 80% of the available water, renewable water for ecosystem services. So I think that resulted in Messer and McConan coming up with an estimate of about 4 billion people subjected to water scarcity at least 1 month a year. So would you like to comment on those things, Junguo, because you also do a lot of work on ecosystems and have done a focus study in a river basin in the Yellow River basin on considering ecosystem services and those aspects.
Oh yes, I can give some comments on these issues. In the water scarcity assessments, the choice of spatial and temporal scales is very important. Earlier water scarcity assessment, for example, the two papers published in Science by Smarty in 2000 and by Oki and Pierce in 2006 are conducted with a spatial resolution of 30 archimedes, about 50-kilometer resolution near the equator on an annual basis. With more data available and further development of models, the assessment of water scarcity has been advanced with higher spatial resolution and monthly time scale. One example is that McNeil and Hofstra assess the global water scarcity on a monthly basis and published the results in 2016. They found that 2/3 of the global population, roughly 4 billion people, live under conditions of severe water scarcity at least 1 month of the year, and nearly half of these people live in India and China. So the estimate of people affected by water scarcity in the above study is notably higher than many other studies. And for other studies, typically the people suffering from water scarcity did not exceed 2.5 billion. I think there are two main reasons. First, McNeil and Hostra's assessment is conducted monthly, accounting for individuals.
So we're having a little bit of a problem with the internet connection, and so maybe I will talk until we get it back, hopefully.
Okay.
So, oh yeah, go ahead. So we're back. Thanks, Junguo.
I mean, can you hear me now?
Yes.
Affected by water scarcity?
I can hear you.
McNeil and Hofstra study is notably higher than many other studies. And for many other studies, mainly the people suffering from water scarcity will not exceed 2.5 billion, but McNeil gave a number of 4 billion. I think there are two main reasons. First, McNeil and Hofstra accounting for individuals experiencing water scarcity even for just 1 month, rather than using the annual averages. The second reason is this study assumes environmental flow requirements to be 80% of the total water resources across all river basins. You mentioned this ratio a moment ago. However, I think this assumption is unrealistically high for many regions globally. The environmental flow requirements vary across flow regimes and seasons within natural systems. For instance, in a study of 11 rivers worldwide, Pasteur and Pierce in 2014 found that the environmental flow requirements to average about 37% of the annual average flow. However, these requirements can range from as low as 25% for rivers in Tanzania to as high as 54% for rivers in Chile. Many studies indicate that assuming environmental flow requirement to be 80% of the natural flow is a realistic assumption, leading to an overestimation of water scarcity. So that explains the higher population suffering from water scarcity from the study of Magni and Hofstra.
Right, right. So thanks for explaining that. And I think, as you say, the 80% requirement of water for environmental flows probably overestimates, because in one of the river basins that you studied, you came up with about 25% in a river basin in North China. So it may be overestimating the number of people subjected to water scarcity. Another aspect, Junguo, that you looked at for the water scarcity is considering both the quality of the water and the quantity. And Michelle Van Vliet has done this in her work, and you also did it for a river basin in North China. Maybe you can describe the results from that, or also considering water quality impacts in southern China.
Okay, sorry. It seems there are some internet problem, and now I'm using my mobile phone for the internet.
Okay.
You mentioned the quality issue related to water scarcity, right?
Right.
Yeah. The traditional water scarcity indicators have mainly focused on water quantity. However, what we need is clean water, not dirty water. So in my team, we've developed novel approaches that account for both quantity-induced and quality-induced water scarcity. The quality-induced water scarcity indicator is defined as the ratio of groundwater footprint to freshwater resources availability. And here, the groundwater footprint represents the volume of fresh water needed to assimilate pollutants based on natural background concentrations and existing ambient water quality standards. So using our approach that integrates both quantity and quality-induced water scarcity, we conducted an analysis of water scarcity for the entire China. And the findings reveal that the northern regions of the country face a challenge from both quantity and quality-induced water scarcity. In the southeastern part of China, quality-induced water scarcity prevails due to severe water pollution. Conversely, in the southwest, there is no apparent water scarcity issue. These results imply that northern China shoulders a heavier burden in addressing water scarcity problems, with quality-induced water scarcity presenting an even greater challenge than quantity-induced water scarcity in many provinces in China. So you also mentioned the case study for the northern part of China. We extended our water scarcity methodology to a quantity, quality, environmental flow requirement approach, abbreviated as QQE. In QQE, we utilize the ratio of blue water footprint to blue water availability to assess quantity-induced water scarcity, and use the ratio of groundwater footprint to water availability to assess quality-induced water scarcity. We also include the ratio of environmental flow requirements to natural flows. And the QQE approach was initially implemented in the Huangqi River Basin in Inner Mongolia in China. The QQE indicator reveals that the the Huangqihai River Basin experienced quantity-induced water scarcity with an indicator of 1.3 exceeding the threshold of 1.0. Moreover, it faced significant quality-induced water scarcity issues with an indicator of 14.2, much higher than the threshold of 1.0. So this assessment is based on an environmental flow requirement level equivalent to 26% of the natural water flows. If a higher environmental flow requirement level is needed, the water scarcity situation will worsen accordingly.
Right. So that was a very interesting analysis, QQE, quantity, quality, and environmental flows. So in that particular basin, then the water quantity scarcity was not that high. It was 1.3 relative, whereas the standard is 1. But the quality, of indicator of 14 means that you would need 14 liters of water to assimilate the pollutants per liter of actual water. So the gray water footprint is very high in that region.
Exactly.
Right. And so, if you look at China as a whole, then as you mentioned, water quantity scarcity is more prevalent in the north, but in the southeast, where you've got a lot of development, a lot of urbanization and industrial development, water quality issues are more a concern. So it's important to consider those different factors. But I mean, in affecting the water quality, then you've also had a lot of economic development, which has brought a lot of people out of poverty in China. And the World Bank report indicated that China achieved the greatest reduction in poverty relative to any country globally, decreasing the number of people in extreme poverty by about 800 million since the 1980s. So I've been talking to Charlie Forrest-Marty in the past, and he said, oftentimes to get that economic development, we impair the water resources, but then repair them afterwards. So I was in the middle of talking about bringing people out of poverty. So China had a marked reduction in the number of people subjected to poverty, decreasing that number by about 800 million since 1980. And that accounted for about 75% of the global poverty reduction over that time, attributed, of course, to rapid economic growth, education, and infrastructure investment. So it seems like maybe China is now shifting to trying to improve water quality. And maybe you could describe that a little bit, Junguo.
Oh, yes. You mentioned the big achievement of the poverty reduction in China. As you mentioned, China has been a remarkable reduction in poverty with nearly 800 million people lifted out of poverty. And certainly, you also mentioned the pollution. Pollution poses a significant threat to sustainability. China has achieved remarkable progress in the prevention and control of water pollution, particularly in the past 10 years. In the year 2015, the State Council issued and implemented the Water Pollution and Control Action Plan, referred to as Water 10, to guide the action for national water pollution prevention and control work, especially for the elimination of black odor water in urban areas. And this marks a historic and a transformative shift in water pollution governance. And the most significant aspect of the Water 10 was the systematic advancement of water pollution prevention and control, aquatic ecosystem protection, and water resources management integrated in a coordinated approach. This plan made notable breakthrough and exploitations in establishing a new mechanism for pollution prevention and control. And another issue is in 2017, the revised water pollution prevention and control law was approved by the National People's Congress and went into effect on January the 1st, 2018. And this new version of the law strengthens government responsibility and supervision. And in recent years, China has implemented two watershed protection laws. The first is the Yangtze River Protection Law, which came into effect on March the 1st, 2021. The second is the Yellow River Protection Law, which officially took effect on April the 1st, 2023. These laws stipulate the state strengthens the ecological protection and restoration of river basins. And the government also enhances the comprehensive management of environmental pollution, implements systematic management, and address pollution at its source while promoting comprehensive treatment of key river and lake environments. So I think these policies play very important roles for the wastewater treatment for the aquatic systems.
Right. So that's really fantastic to see that progress and that emphasis on pollution control. You also lived in Shenzhen for a number of years when you were a professor at the Southern University of Science and Technology there. And Shenzhen really grew very rapidly over the past 20 years, but they also have achieved a great reduction in pollution there in black, as you mentioned, black odorous rivers. And also I saw mention of, sponge city concept to reduce flooding in these regions. Maybe you can describe that a little bit and what happened in Shenzhen.
Okay, so at the beginning of 2016, among the 310 rivers in Shenzhen, there were as many as 159 black and odorous water bodies, so more than half. And the water quality of the 5 major rivers was very bad. And since 2016, the Shenzhen government has launched a comprehensive battle against water pollution, promoted the fundamental and historic improvement of water environment quality. In the process of cleaning the Mozu River, that is the mother river of Shenzhen, our framework of stepwise ecological restoration plays a key role. And this framework requires selecting tailored restorative modes, setting clear restorative targets and reference ecosystems, applying a systematic thinking approach, and implementing a continuous monitoring program at all the processes. Shenzhen became the first city in China to eliminate black and odorous water bodies in November 2019, with 159 black and odorous water bodies and 1,467 small-scale black and odorous water bodies. all the water bodies have been treated, and the water quality of the mother river, the Mozu River, has reached the best level in history since monitoring data were available. The ammonia concentration for the Mozu River witnessed a significant decline from about 34 milligram per liter in 2011 to 1.3 milligram per liter in 2020, showing the significant improvements in water quality. You also mentioned the sponge city. China initiated the development of sponge city in the year 2013. This became a new solution for urban stormwater management. The government issued a series of related policies and guidelines for the sponge city development in an effort to improve the sponge city construction. And in addition, China central government selected 30 pilot cities considering their different natural and social conditions for the sponge city construction in 2015 and 2016. And in 2021, based on the experiences of pilot cities, China began to systematically promote the sponge city demonstration on a national scale. And Shenzhen City is a pilot city for the sponge city construction. Definitely, the China Sponge City initiative is a very typical nature-based solution. It has a very ambitious goal. By 2020, 80% of the urban areas should absorb and reuse at least 70% of the rainwater. The construction of the sponge city emphasizes the full use of the natural absorption and infiltration capacity of the pervious areas to effectively control stormwater runoff and minimize the water system problems caused by the damage of urbanization-induced hydrological effects. And the philosophy of the sponge city is to transfer the traditional fast drainage principle to a systematic implementation of infiltration, detention, retention, purification, utilization, and discharge. So it's a typical nature-based solution. And for the Shenzhen city, the government used both the green infrastructure or the human-built infrastructure for wastewater treatment, and also the nature-based solutions to solve the pollution issue.
That's incredible. So they have really come along with reducing pollution, and Shenzhen is a remarkable example. So is that by reducing discharges from industry, and maybe they're recycling more of the water within these industrial complexes? And then are they installing synthetic wetlands to assimilate the contaminants? And the sponge city concept, is it increased permeability of the pavement in addition to the green infrastructure? I'm not really that familiar with the sponge city concept. So to achieve this, then, I guess it's done in a number of ways. Are there many more water treatment plants installed to treat the water, and then also try to stop it at its source at the industry by recycling more of the water at those industrial complexes?
Yeah, definitely the wastewater plant treatment play a very important role for reducing the amount of pollutants in the Shenzhen city. But in addition to this, the government use different approaches like the sponge city and also the construction of wetland to deal with the pollution issue. So it's a combination of the green solution with the green solution.
Right. Well, that's great. And I know Charlie Vorsmarty promotes this combined hybrid green gray infrastructure. So green nature-based solutions and gray traditional wastewater treatment and all of that sort of thing to achieve this reduction in pollution. So, we've talked about a lot of different things, water quantity, water quality, both impacting scarcity and then environmental flow requirements. But if we get back to trying to resolve some of the water scarcity issues in China, you mentioned in one of your papers, the relative importance of physical transfers of water, like the south to north water transfer, and also virtual water transfers through food trade in China. Maybe you can describe those a little bit, Junguo.
Okay, thank you. We can supply more water through either physical water transfer project or virtual water transfers. And the virtual water transfers in the process of food trade from exporting to importing regions. We can supply more water through either physical water transfer project or the virtual water transfers. And the virtual water transfers are in the process of food trade from exporting to importing regions. And in our study, we compared the magnitude of physical and virtual water flows in China. And this research was published in PNAS in the year 2015. And for our study, we found that China has been developing over 20 major physical water transfer projects with a total length of over 7,200 kilometers. For example, the largest one is the South to North Water Transfer Project. And this project aims to bring up to 45 cubic kilometer of water annually with through routes. And based on our calculation in the year 2007, physical water flows by water transfer projects in China amounted to 26 cubic kilometer, accounting for 4.5% of the national water supply in China. And the total volume of virtual water flows was about 200 cubic kilometer in the same year, and they accounted for 35% of the national water supply. So this means virtual water flows were much higher than physical water flows through the transfer project. We also noticed that the virtual water flowed from the economically poor and less populated west to the more rich and densely populated coastal areas of the east, where most of China's megacities are located. Virtual water flows helped to solve water scarcity problems in many regions in eastern part of China, but they exacerbate the water stress for the water exporting regions, such as the Inner Mongolia in the north, Xinjiang province in the northwest, and the Heilongjiang province in the northeast. And well, about the direction of the virtual water flows, we can see there is a trend from the west to the east. But the west, we have very limited water resources. So we also want to know why such a pattern happens in China. we found that it is not only the availability of water that drives the direction of water flows. In our recent study published in 2019 in Water Research, we found that the regional differences in land productivity are the main forces determining the pattern of water flows across major regions in China, and other sources such as labor and water have played only very limited role. So this also explains why water goes from water-limited northwest China to many eastern regions.
Right. And so, I mean, you mentioned that in 2007, there was 26 cubic kilometers of water for physical water transfers. And for the US listeners, that would be about, similar to 26 million acre feet, which is the unit that we use, 1.2 million acre feet, or cubic kilometers per million acre foot. And for context, then, Texas uses about 17 million acre feet a year of water. So, but with the south to north water transfer then, which has been developing over since 2007, they're projected to transfer up to 45 cubic kilometers of water from the south to the north, and estimated cost of about 600 billion. But as you say, virtual water transfers through food trade are generally much larger than the physical transfers. But transferring food from water scarce regions to the east, more urbanized areas is exacerbating water scarcity problems in the northwest. And I guess it's similar in the US. I mean, we trade a lot of food from California, which is from semi-arid regions in California, and results in a lot of groundwater depletion to other parts of the US. So that sort of trend happens here also. So you've also, so that kind of leads us to food production. You've also examined issues with the global crop water productivity and focusing on wheat production, which is a very nice analysis, and looking at the crop water productivity, comparing actual yield to actual evapotranspiration using the EPIC code with the GIS combination that you refer to as GEPIC. So maybe you can just describe a little bit on crop water productivity and how that varies globally, and how fertilizers, and then that leads to your work on fertilizer applications and impacts on the environment from that. Maybe you can describe those a little bit, Junguo.
Okay, thank you. So the crop water productivity is defined as the crop yield over actual evapotranspiration, and it reflects the amount of crops that can be produced with a unit of consumptive water use. As you mentioned, we simulated crop water productivity of wheat with the GEPIC model. GEPIC is a GIS-based environmental policy integrated climate model, and it is an integration of the EPIC model developed in the US with the GIS system. So with the GEPIC model simulation, we provide a global map of wheat yield and also global maps of crop water productivity. And we found the highest yields in Western Europe and relatively high yields in Northern China, Eastern Europe, and the lowest wheat yields were found in many African countries. When we look at the crop water productivity, we also found that the regions with high crop yields often are the regions with high crop water productivity. So in order to examine the effect of water availability and fertilizer application on crop yield and crop water productivity, we use the GAPIC model to simulate the situation with sufficient water and fertilizer supply holding other factors unchanged. And this will lead to the potential yield. And most European countries have the potential to achieve wheat yields over 7,000 kilograms per hectare, and the crop water productivity over 1.2 kilogram per cubic meter. And the gap between the currently achieved yield and crop water productivity and their potentials is relatively very small. This reflects that the fact that in many European countries, water and supply and the fertilizer supply and other management factors are already in near optimum conditions. In contrast, the large gap appears in many African countries. Our results with crop water productivity between 1.2 and 1.8 kilogram per cubic meter if the water supply and fertilizer application was sufficient. But the current yield is very low, and the current crop water productivity is also very low, relatively lower than 0.8. So the high potential yields and crop water productivity suggests that increasing water and fertilizer supply would significantly improve wheat production in Africa, although other management factors may also have to be improved.
Right. So this was very insightful. And I think when you summed up over the global scale, you estimated that the global virtual water export was about 160 cubic kilometers. And if you estimate the global virtual water import, what it would require to grow those foods in the importing countries would be about 240 cubic kilometers. So it suggests that you're saving about 80 cubic kilometers by trading food from more water-rich areas to places where it would take more water to grow those foods. Is that correct, Junguo?
Yeah, it's correct. As you mentioned, about 130 million tons of, well, for the wheat, we only start for this study, we only focus on wheat. And in 2000, about 130 million tons of wheat was traded in the international food market. And our calculation shows that the global water import of 240 cubic kilometer and global water export of about 240 cubic kilometer, the difference of about 80 cubic kilometer represents the global water savings through wheat trade in this year. And then we want to know why there is a water saving through the international trade of wheat. We found that the top 5 exporting countries, namely USA, Canada, France, Australia, and Argentina, they were responsible for about 80% of the wheat export. And except for Argentina, the other major exporting countries all have crop water productivity values higher than 0.8 kilogram per cubic meter. And in contrast, the top 5 importing countries, namely Brazil, Italy, Iran, Japan, and Algeria, have values of crop water productivity lower than 0.6 kilogram per cubic meter, except for Italy. So the difference in crop water productivity among the importing and exporting countries resulted in the global water saving through the international wheat trade.
Well, that's really interesting. And then I guess the last aspect that I would like to discuss briefly, Junguo, is your work on fertilizers, because you mentioned the food scarcity issues in Africa, a lot to do with water scarcity and fertilizer scarcity. So you did a global analysis on fertilizer applications, mineral fertilizers, and other sources of fertilizers, and then looked at nitrogen fertilizer, virtual nitrogen trade also. Maybe you can describe that a little bit.
Okay, yeah. The crop production is the single largest cause of human change to the global nitrogen cycle. And we give a comprehensive assessment of the global nitrogen flows in cropland with a spatial resolution of 5 acre minutes, about 10 kilometers near the equator. And according to the article published in PNAS in 2010, the total nitrogen input in cropland was about 136.6 trillion grams in the year 2000. And the nitrogen input from mineral nitrogen fertilizer was the single largest nitrogen input in cropland, accounting for almost half of the global nitrogen input. Biofixation from soybeans, legumes accounted for 16% of the nitrogen input, while manure, recycled crop residues, and atmospheric deposition provided similar amounts of nitrogen, with each contributing 8 to 13% of the total input. And based on our estimate, the total nitrogen output from cropland was about 148 trillion grams of nitrogen in the year 2000. Of which 35% is uptake by harvested crops, 20% uptake by crop residues, 16% lost through leaching, 15% lost through soil erosion, and 14% through gases emission.
So that's very interesting. Half of the nitrogen comes from fertilizers, and then some comes from biofixation with the leguminous crops, and then you've got some contribution from manure and crop residues and atmospheric deposition. But so you estimated that about 80% of African countries are subjected to nitrogen scarcity, which results in food insecurity and malnutrition. And the mineral fertilizers in Africa and much of South America is only 25 to 30%, whereas the average globally is about 50%. So the high nitrogen output with crop yield in Europe and the Midwest US and South China, Southeast Asia, accounts for is related to a lot of food exports from those regions. And the nitrogen recovery rate, you estimate globally, is 60%. That means 40% is lost to ecosystems, and that really impacts ecosystem health. Maybe you can explain that a little bit, Junguo.
Okay, yeah. So a lot of information for this. And for the nitrogen scarcity, in fact, we learned from the assessment of water scarcity. We define the nitrogen scarcity as the total nitrogen inputs into cropland. And if the level is lower than 9 kilograms per capita per year, and we can define this as the nitrogen scarcity. If the nitrogen input level is between 9 and 15 kilograms per capita per year, we define the region as a region with nitrogen stress. And for our results, we show that almost 80% of African countries are suffered from nitrogen scarcity or the nitrogen stress problems. And this can influence the poverty, food insecurity, and malnutrition. And one key reason for the nitrogen scarcity in Africa is the low level of fertilizer application in Africa. And the input from fertilizer only accounted for 25% of the total inputs in Africa, but this ratio can be as high as 55% in Asia and 48% for North Africa. So this means that in order to address the nitrogen scarcity issue for Africa, many countries, they need to increase the application rate of fertilizer.
But I guess that problem is amplified these days with the high cost of nitrogen fertilizers, with energy issues, and particularly in Africa, where transport of most of the fertilizers are imported, and then you have large costs for transporting the fertilizers to smallholder farmers and things like that. So all of these things amplify the problem.
Exactly. The fertilizers are very expensive in Africa. The prices are much higher than those in China or in US. The key reason is like what you mentioned, the poor infrastructure in Africa, because many African countries, the capacity to produce fertilizer is low. They have to rely on fertilizer import. And when the fertilizer imported to the harbors in Africa by boat, and they have to be transferred again from the coastal area to the farming area. But because of the poor transportation and the poor infrastructure, it will take a lot of money to transfer the fertilizer to the farming area. So this leads to the very high prices of fertilizer.
And I guess one last point, Junguo, to kind of link the water scarcity with the nitrogen issues is that when you were looking at virtual water trade in China through food trade, you were exporting food from water scarce regions to the East Coast, where it's mostly urbanized. But in terms of global food exports related to nitrogen issues, most of the big food exporters like US, Canada, Australia, and France, they have nitrogen sufficiency. So food trade, so you're exporting food from regions with nitrogen sufficiency to regions that don't have it, like countries like Japan, with big importer of food and nitrogen, related nitrogen.
Yeah, you're correct. The big food exporters like the US, Canada, Australia, Argentina, and France, they had nitrogen sufficiency. And the higher per capita nitrogen input partly contributed to the exports of agricultural products in these countries. And Japan had nitrogen scarcity with a total nitrogen input even lower than 5 kilograms per capita per year, but the malnutrition percentage was very low in Japan. This is because Japan imported a large amount of food from international markets, and it lacks the arable land to feed its own population in Japan. Importing food is equivalent to importing nitrogen from other countries for the purpose of domestic consumption of nitrogen. And the nitrogen obtained from food trade can be termed virtual nitrogen. This term is very similar to the term virtual water. And it is also helpful to study to what extent the domestic nitrogen scarcity in food importing countries was mitigated by virtual nitrogen. As a typical example, Japan relied heavily on food and nutrient imports to meet its domestic caloric needs, and about 88% of its needs were obtained from imported commodities. And in contrast, Africa imported 26% of the total fertilizer consumed, and the low fertilizer inputs and the low capacity of food imports lead to a lot of malnutrition problems in Africa. So when we work on the virtual nitrogen flows among different regions, we can get very interesting results by looking at the situation in different countries.
Right. Well, thank you so much, Junguo. Our guest today was Junguo Liu, who's the president of North China University of Water Resources and Electric Power. And we've been discussing Junguo's research on water scarcity, global wheat production and food production, and global nitrogen cycling related to food production. So I commend you on fantastic analysis of these data, and really advances our understanding of the impact of trade, food trade, then in resolving some of these disconnects between supply and demand. So thank you so much, Junguo, for your time.
Thank you very much for your interview, Bridget. Thank you.